What is time? It's a question that has puzzled philosophers and scientists for centuries. Is it simply the ticking of a clock, a way to measure the passing moments? Or is time something far more profound, a fundamental aspect of the universe we inhabit? We feel its passage every day, yet it remains an enigma, a concept that is both familiar and deeply mysterious. From our earliest memories, time flows in one direction, from the past, through the present, and into the future. But why is this so? What sets the direction of time's arrow? These questions have captivated thinkers for generations, leading to a quest to unravel the true nature of time. In this exploration of time, we'll delve into the realm of physics, seeking answers in the laws that govern the cosmos. We'll embark on a journey to understand the strange and fascinating aspects of time that have intrigued scientists and stirred the imaginations of dreamers. Time is not merely an abstract concept, it is woven into the very fabric of our existence. It dictates the rhythm of our lives, from the rising and setting of the sun to the beating of our hearts. Our understanding of the universe, from the smallest atoms to the largest galaxies, hinges on the concept of time. In physics, time is not just a measure, it's a dimension, a fundamental aspect of reality. Just as we navigate through three dimensions of space length, width, and height, we also move through time. This concept, known as spacetime, is crucial to Einstein's theory of relativity, a cornerstone of modern physics. Einstein's groundbreaking work revolutionized our understanding of time, showing that it's not absolute but relative. Time can be stretched and compressed, its passage influenced by gravity and motion. This mind-bending concept has profound implications for our understanding of the universe. Prepare to embark on a journey into the strange and wonderful world of time, where the familiar rules of everyday experience are bent and sometimes even broken. We'll explore the mind-boggling implications of time dilation, a phenomenon where time slows down at incredibly high speeds or under the influence of intense gravity. Imagine a pair of twins separated at birth. One twin remains on Earth, while the other travels through space at near the speed of light. When they reunite, the spacefaring twin will have aged less than the Earthbound one. This is time dilation in action, a consequence of Einstein's theory of special relativity. Our journey will take us to the edge of black holes, where gravity is so strong that time itself seems to grind to a halt. We'll delve into the mysteries of the quantum realm, where the very nature of time becomes uncertain and fluid. To grasp the true nature of time, we must venture beyond our everyday perception of it as a simple progression from past to present to future. Physicists view time as a dimension, an integral part of the fabric of the universe. Just as we navigate through three dimensions of space length, width, and height, time serves as the fourth dimension. Imagine a point in space. It has no size or shape, it simply exists at a specific location. Now, extend that point forward, and it traces a line representing one dimension of space. Extend that line in a perpendicular direction, and you create a flat surface representing two dimensions. Add height to that surface, and you have a three-dimensional object. Now, picture that three-dimensional object existing across a span of time. It changes and evolves, its history unfolding moment by moment. To pinpoint its location in space-time, you need to specify not only its coordinates in space, but also its position in time. This concept of space-time is fundamental to understanding the universe as described by Einstein's theories of relativity. Einstein's theories of special and general relativity revolutionized our understanding of time and its relationship to space. These theories revealed that space and time are not separate entities but are interwoven into a single, unified fabric, space-time. This fabric is not static, it can be warped and curved by the presence of mass and energy. Imagine space-time as a trampoline. If you place a bowling ball in the center, it will create a dip in the fabric. Similarly, massive objects like stars and planets create distortions in space-time. These distortions are what we experience as gravity. Just as the bowling ball's weight determines the depth of the dip in the trampoline, an object's mass dictates the degree to which it warps space-time. The more massive the object, the greater the curvature. This curvature of space-time influences the motion of objects, including light, causing them to follow curved paths. One of the most perplexing aspects of time is its apparent unidirectionality. We experience time as flowing inexorably forward from past to future. This perceived directionality is often referred to as the arrow of time. But what causes this arrow to point in one direction, and why can't we reverse its course? In the macroscopic world, the arrow of time is evident in countless everyday phenomena. A dropped glass shatters, but the shards never spontaneously reassemble. We age and our bodies deteriorate, but we never grow younger. These irreversible processes seem to define the direction of time's arrow. However, the fundamental laws of physics, with a few exceptions, are time symmetrical. This means that they work equally well whether time runs forward or backward. So why do we observe this asymmetry in the macroscopic world when the underlying laws don't seem to dictate it? The key to understanding the arrow of time lies in a concept called entropy. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of a closed system can only increase over time. In other words, things tend to become more disordered. Think of a tidy room. Over time, without any effort to maintain order, it will inevitably become messy. Clothes will be strewn about, books will pile up, and dust will accumulate. This increase in disorder is a manifestation of entropy at work. The connection between entropy and the arrow of time is profound. The universe as a whole is constantly moving towards a state of higher entropy. It's like a giant clock that can only wind down, not up. This relentless increase in entropy provides a directionality to time, pushing it from a past of lower entropy to a future of higher entropy. While the arrow of time, driven by entropy, seems to point resolutely forward, the possibility of time flowing backward or even standing still has captivated the imaginations of physicists and science fiction writers alike. Could we ever hope to travel through time, to revisit the past or leap into the future? Einstein's theories of relativity, which paint a flexible and malleable picture of spacetime, offer tantalizing hints that time travel might not be entirely implausible. These theories suggest that time is relative, its passage varying depending on factors like speed and gravity. However, the practicalities and paradoxes associated with time travel present formidable challenges. The concept of causality, the idea that cause must precede effect, is deeply ingrained in our understanding of the universe. Time travel, if possible, could potentially disrupt this fundamental principle, leading to mind-boggling paradoxes like the grandfather paradox. Albert Einstein's theories of special and general relativity revolutionized our understanding of time and space. Special relativity, introduced in 1905, proposed that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum is constant, regardless of the motion of the light source or observer. This led to the groundbreaking realization that time is not absolute, but relative. In special relativity, time can vary depending on an object's velocity. This means that clocks moving at high speeds relative to an observer will tick slower compared to those at rest. This phenomenon, known as time dilation, challenged the traditional notion of time as a constant, unchanging backdrop to events. General relativity, published in 1915, extended these ideas to include the effects of gravity. Einstein proposed that massive objects cause a distortion in spacetime, which is experienced as gravity. This warping of spacetime affects the passage of time, causing clocks closer to massive objects to tick more slowly compared to those further away. These theories have profound implications, suggesting that time is intertwined with the fabric of the universe. The implications of relativity extend far beyond theoretical physics, affecting everything from satellite technology to our understanding of the cosmos. Time dilation is a fascinating prediction of Einstein's theory of relativity. Time passes at different rates for observers in different frames of reference. Consider a light clock that measures time by bouncing a beam of light between mirrors. If the clock moves, the light beam travels a longer diagonal path. Thus, time appears to pass more slowly for the moving clock. Time dilation also occurs near massive objects due to space-time curvature. One of the most famous thought experiments illustrating time dilation is the twin paradox, Imagine two identical twins. One remains on Earth while the other embarks on a journey through space at nearly the speed of light. According to special relativity, the traveling twin will experience time more slowly than the twin who stays on Earth. Upon the traveling twin's return, they would find that they have aged less than their Earthbound sibling. This apparent paradox arises from the fact that the traveling twin has undergone different inertial frames during their journey, particularly during acceleration and deceleration phases, whereas the stay-at-home twin has remained in a single inertial frame. The twin paradox highlights the non-intuitive nature of time dilation and the relative nature of time. It underscores the principle that time is not a universal constant, but is instead influenced by relative motion and gravitational fields. This thought experiment, while seemingly paradoxical, has been supported by experimental evidence. High-speed particles in accelerators and precise atomic clock measurements on fast-moving aircraft and satellites have all confirmed the predictions of time dilation, reinforcing the principles of relativity. Gravitational time dilation is a phenomenon predicted by Einstein's general relativity. Time passes more slowly in stronger gravitational fields. Imagine space-time as a flexible sheet. A heavy ball creates a deep well, representing a strong gravitational field. A clock near this well ticks more slowly than one far away. This effect is crucial for the accuracy of the Global Positioning System, GPS. GPS demonstrates time dilation in action. Satellites with atomic clocks transmit signals to ground receivers. Special and general relativity affect GPS operation. Satellites move at 14,000 kilometers per hour at 20,000 kilometers altitude. Without corrections, clocks would diverge by 38 microseconds daily. GPS systems correct for these effects to ensure accuracy. Black holes, remnants of massive stars, create extreme environments for studying time dilation. Near the event horizon, time slows dramatically for an external observer, while an astronaut would experience time normally. These extreme cases highlight the profound effects of relativity on our understanding of time. Our personal experience of time is often subjective, racing by when we're engrossed and dragging when we're bored. This elasticity of time is influenced by our emotions and mental state. Flow state occurs when we're so engaged in an activity that we lose track of time. Our perception of time changes with age and experiences. Children often feel time moves slowly, while adults feel it accelerates. Cultural factors also shape our attitudes towards time, influencing how we structure our days. A network of brain regions, including the hippocampus and prefrontal cortex, are involved in our perception of time. Emotions like fear and joy can alter our perception of time, making it seem to slow down or speed up. Some philosophers argue time is an illusion created by our minds, while others believe it is a fundamental aspect of reality. The debate about the nature of time continues, reflecting our quest to understand our place in the cosmos. Stepping into the time machine. A scientific possibility? Einstein's theories of relativity suggest time travel might not be entirely implausible. Time dilation, verified by experiments, shows time is flexible and malleable. General relativity introduces spacetime, where massive objects warp the fabric of space and time. Wormholes, tunnels through space and time. Wormholes, theoretical tunnels through space-time, could connect distant points in space and time. While their existence is speculative, they remain a fascinating concept in theoretical physics. The grandfather paradox highlights potential contradictions in backward time travel. It challenges our understanding of cause and effect, suggesting complex interconnections between past, present, and future. The grandfather paradox has led to proposals like the Novikov self-consistency principle, which suggests the universe prevents paradoxes. Another idea is time travel to parallel universes, where actions don't affect the original timeline. These speculative ideas reflect ongoing research into the nature of time and time travel. Physicists explore the boundaries of time, with experiments on time dilation and potential microscopic wormholes. The ethical implications of time travel raise profound questions about free will and reality. Understanding time is a journey of self-discovery, deepening our appreciation of our place in the cosmos. The dream of time travel reflects our curiosity about the past and future. It promises second chances and glimpses of the future, inspiring scientific exploration. While speculative, the dream of time travel continues to push the boundaries of our understanding. As we contemplate the nature of time, we must shift our perspective to the grand scale of the cosmos. Cosmic time dwarfs even the most extended human lifespan. Imagine the universe's entire history compressed into a single year. The Big Bang occurs at the stroke of midnight on January 1st. Our solar system forms in late August and life appears in September. All of recorded human history fits into the last few seconds of December 31st. Our lives are fleeting moments in the grand scheme of cosmic time. Just as our individual lives are governed by the flow of time, so too is the universe subject to the relentless march of entropy. The second law of thermodynamics, one of the fundamental laws of physics, dictates that the total entropy of a closed system, such as the universe, can only increase over time. Entropy, often described as a measure of disorder or randomness, dictates that systems tend to move from a state of order to a state of disorder over time. Think of a tidy room that gradually becomes messier unless energy is expended to maintain its order. Similarly, the universe is slowly but inexorably moving towards a state of maximum entropy, a state often referred to as the heat death of the universe. As the universe expands and cools, stars will eventually exhaust their nuclear fuel and die out. Black holes will slowly evaporate through Hawking radiation, and the remaining matter and energy will become more evenly distributed, leading to a state of thermodynamic equilibrium. In this final state of maximum entropy, no more work can be extracted from the universe. Temperatures will be uniform, and no significant events will occur. Time, in a sense, will lose its directionality, as there will be no distinction between past, present, and future. The concept of the heat death of the universe raises profound questions about the ultimate fate of time itself. If the universe reaches maximum entropy, does time cease to exist, or does it continue to flow, even without events? Some physicists speculate that the heat death might not be the end. Perhaps our universe is just one in a vast multiverse. The end of our universe might mark a new beginning. Others propose cycles of expansion and contraction. In these models, time might exist as an eternal loop. These ideas remain highly speculative. Our understanding of the universe is incomplete.